All right, this one I'm going to take a guess is going to be a slightly longer one. So let's now consider more general oscillations that might have some dampening or might have some driving. But let's remind ourselves kind of where we started, right? We started with a simple harmonic motion differential equation, which when solved gives a solution that oscillates in time, given by a trig function that has some amplitude, some angular frequency, some phase angle as a function of time. And we had a couple examples last time where this was perhaps an approximation, like take, for example, the pendulum. For the pendulum, we had an example where we were solving an approximation equation where when sine of theta was sufficiently small, that became theta, and we could allow it to be simple harmonic motion instead. And I thought quickly I'd show some pictures, or if you were to solve this on a computer, what this would look like. So I'm going to show two cases of kind of the motion as a function of time of kind of the angular displacement of a pendulum. This first case is going to be the case where the initial angular displacement in radians is pretty small, and then there'll be one where it's large, and you can see how it starts to deviate. So here's the case where the angular displacement is pretty small, and the actual true solution is kind of this red dotted line. That is the actual motion of the pendulum. And on top of it, I'm showing as a black line what you would expect if it were simple harmonic motion. So the black line is just me plotting cosine, where the red curve is the actual solution to the differential equation. And you can see that they pretty much are in perfect agreement, where you can start to see actually a little bit of deviation as you go on. So they start really close to one another, but it seems like as you go on and on and on, they are starting to ever so slightly deviate from one another. And if you were to make the angular displacement initially even smaller, it would take even more time before you started noticing this deviation. Compare that to if you have a larger angular displacement, so 0.75 compared to 0.25, where again, and again, this is the true solution where the black is just me plotting a cosine function. Notice that, again, they start in agreement. The pendulum swings, if negative is to the left, it swings to the left, and starts swinging to the right. And the solution is overall still oscillatory. But notice that after one period, more or less, you start to see significant deviations from the cosine solution versus the actual solution. And if you make theta, the initial theta, bigger and bigger and bigger, these deviations become even more and more pronounced, that the red curve actually starts to stretch out as well. And it turns out that the true solution, once you get big enough, the period does depend on the amplitude. And we can see that here, right? In this case, it seems like the period is more or less the same, but then there's deviations that become more and more and more. So you can see how there's the actual period of the red curve is different compared to the period of the black curve, which did not depend on the amplitude. Where in this case, for the red curve, there does seem to be a slight amplitude dependence, where here the deviation seems to be much, much smaller. So that's some examples of simple harmonic motion without dampening, and how it compares to general oscillatory motion. Now let's add dampening back in by assuming that there's some sort of friction force that opposes the direction of velocity. So something simple like a 1D friction force, where then the equation of motion might be mx double dot equals negative kx, but then also negative bx dot as well. So the differential equation, once you divide through by m, looks like it's b over m times x dot, and then there's again the k over m times x equals 0. This is still a linear, homogeneous, second-order differential equation. You can still solve it with the exact same methods as we did before, but now there's this additional term, which is going to appear in the auxiliary equation. We're going to write, again, k over m as omega naught squared, which we're going to call the natural frequency. The frequency of the oscillations when you are not dealing with dampening, it depends on properties of the system, right? The mass, the spring constant. We saw before for the pendulum, it depends on the length of the pendulum and gravity. So that's kind of the natural, right? Let nature do its thing frequency it wants to oscillate around. But when there's dampening, that is thwarted because dampening is ultimately trying to diminish the oscillations. So similarly, we're going to write B over M as 2 times beta, where beta is going to be the dampening constant. Which looks like, by advanced mathematics, is B divided by 2M in this case. It also has units of 1 over seconds. So we're going to see that it's going to play a role where we're also going to see beta times time appear in the final expressions as well. It has the same unit as the natural frequency. So again, how do you solve that? The usual approach to solve, where x double dot plus 2 beta x dot plus omega naught squared times x equals 0. You assume the solution is an exponential. That gives you an auxiliary equation of r squared plus 2 beta times r plus omega naught squared equals 0. That implies that r equals negative 2 beta plus or minus 4 beta squared times minus 4 omega squared, all in the square root. I'll divide by 2. Again, why did we have it be 2 beta instead of just beta? Well, again, it was just a convention that we made, because if we called it 2 beta, then notice that there's a 2 everywhere because the square root of 4 is 2, and this just becomes negative beta plus or minus the square root of beta squared minus omega naught squared, all in the square root, as your 2 possible values of r. So then the general solution, x as a function of t, is going to be, you take each of these values for r, you throw that in the exponential, it ultimately becomes something that looks like e to the negative bt, or beta times t, then there's a, e to the, and then there's the square root business, beta squared minus omega naught squared times t, plus second constant of integration, beta squared minus omega naught squared. There's a negative sign out front in the exponential. This is the general solution. It's not super illuminating, admittedly. We do notice some things, like there's this overall dampening. We know that as time goes on, that thing out front is going to plummet to 0. So you can imagine that's probably having some sort of role of dampening the entire thing away. Because you can show that the thing in the brackets, the exponentials in those brackets, the thing in the square root is necessarily less than beta, unless it's complex. So this entire thing should damp away, as you might expect from there being friction. But again, we can look at the possibilities of, break these into certain cases, depending on the value of beta. Well, there's undamped, which we've already solved. And that's the case when beta equals 0. In that case, x of t is just e to the 0 is 1. So the square root thing just becomes omega naught. This thing just becomes simple. Actually, that's not true, because if beta is 0, that thing in the square root is all complex numbers. So those would have been complex exponentials, which again we can use Euler's identity and rewrite it as a single cosine rather than a sine and a cosine. So it's, of course, simple harmonic motion. The next case to consider is weak dampening, or what's sometimes called underdampening. And that's when beta is less than omega naught. So you can consider this as a case of weak friction. Beta is small. Well, in this case, if beta is less than omega naught squared, that thing inside the square root is going to be negative. So if I take the square root of -1, right, that's the same thing if I flip it, so that's positive, and then there's the square root of -1, which is just I. And I'm going to define this as omega 1 times I. Where omega 1, this is kind of the damped frequency. Which, if beta is small, notice that omega 1 is going to be less than omega naught. Close, but not equal to omega naught. Right, you can imagine as beta goes to 0, it actually becomes omega naught identically. So in this case, the general solution, x as a function of t, is then going to be a e to the omega 1 times t times I plus b, omega, or I guess in this case, negative omega 1 t times I. So in this case, since it's an exponential that has a complex function, like we talked about before, you can ultimately write this as, I'm sorry, I forgot a beta somewhere, right? There's a beta overall. There's that e to the negative beta times t overall. But that thing in the bracket, like what we did for simple harmonic motion, we can rewrite that as a trig function. So I'll write this c cosine of omega 1 times t plus phi. That's all being multiplied by e to the negative beta times t. So you got something that looks like oscillation, right? Because it's the cosine, right? That thing will oscillate, but ultimately damps down to 0. That exponential out front ultimately kills you off. So if we were to plot this, without dampening, we expect something that might look like this. But with dampening, we might expect something that does that overall. It gets smaller and smaller and smaller because of that exponential, and you actually can show that everything is kind of bound within these two brackets that are shrinking, where those dotted lines are plus or minus e to the negative beta times t. Since the cosine can only be at most equal to u, or I guess it would be plus or minus whatever the value of c is times e to the minus beta t. Since cosine can only range between 1 and -1, this entire thing, as it shrinks, can never be greater than whatever c times e to the minus beta t is equal to. And notice it's oscillating at a different frequency. It's not oscillating at omega naught, but it's oscillating at omega sub 1, which is slightly different. So, which is why I also did not put the peaks and the troughs at exactly the same spot in this drawing. The interpretation here is that notice the overall dampening comes as e to the negative beta t. And again, this makes sense because beta, we said, had units of 1/seconds. So the exponential, the thing in the exponential, is ultimately unitless, as it must be. So 1/beta has units of time. So 1/beta is kind of the characteristic decay time for the oscillator. The amount of time it takes the oscillator's amplitude excuse me, to decrease to 1 over e, its current value. Multiplicatively diminishes over time. Three of the cases overdamped. You can think of this as a case where there's lots and lots of friction, where beta is greater than omega naught. In this case, the thing in the square root is positive, so there's nothing wrong with that. There's no complex exponentials that appear. And we can define this new frequency as beta squared minus omega naught squared as some new damped frequency, which could be dramatically different than omega naught, because beta can be anything that's greater, right? Beta could be substantially greater, and this frequency is going to be very different compared to omega naught. Turns out, though, that thinking of it as a frequency really doesn't matter, because when you write the general solution, there's the e to the minus beta t, and then there's the omega 2 times t plus b e to the minus omega 2 times t. But again, since omega 2 is less than beta, that overall e to the negative beta wins out. That second term, the e to the minus negative e to the negative omega 2 times t, is already dying off, but both of these should die off. So if we were to plot this, or maybe you're launched from the origin, right? You kind of shoot up, but then oscillations kind of drive you back down, and ultimately you just get an exponential. There are no oscillations. Notice there's no sines and cosines. So even though it might be a spring in the box, but the box is moving through sand rather than just sliding on a surface, no oscillations occur. Right, this kind of friction force is really pushing the oscillator outwards. And it decays. If you want to define a decay parameter, maybe you could define it as beta minus omega sub 2 or something like that. It's sometimes used, but ultimately there's no oscillations. There's lots of friction, so as the box is trying to get back to the equilibrium spot, the friction is really resisting it, trying to move at all. So it could potentially very, very slowly make its way back to the origin without any desire to oscillate. The last case is the critical case. Something that's critically damped, where beta equals omega naught. In this case, both the auxiliary values are equal to negative beta, because it's plus or minus the square root of 0 in this case. So it is two identical values. So recall that in this case, the general solution is a e to the negative beta t plus b times t e to the negative beta t in this case. So again, you get something that's an exponential decay. And it turns out this actually is a quite rapid exponential decay. So if you kind of launch from rest, you kind of very quickly exponentially decay and come down. So this is very fast decay. And again, no oscillation. So you might wonder why in this case where it's critically damped, where the friction equals the natural frequency, why is that where it decays the fastest? Shouldn't it be when you have lots and lots of friction that you get very rapid decay? Well, not really actually. And let me actually bring this example out before I talk about this. So here's kind of the three solutions all plotted for the same oscillator. So the black curve kind of shows when there's no dampening at all, it just undergoes simple harmonic motion. You don't have to worry too much about the values on the axes. The blue dash is when I have it being, I should have written underdamped in this case, where I have some friction but not a lot of friction. Notice this case, it oscillates, but it ultimately kind of dies down. And the peaks, it's kind of hard to see, but the peak is not exactly at the same location. So it is oscillating at a different frequency than it is when it's simple harmonic motion. I can calculate for the values I simulated the critical damped case where beta equals omega naught, and that is kind of this orangish gold curve, and it just drops down very rapidly. Compared to when I overdamp, where I just have there be even more friction, and notice it indeed decays slower than the critical damp case. So why is the critical damp case the case that decays the fastest? Well, in this case, essentially, you have enough friction so that you don't get oscillations anymore. But you don't have so much friction that if you think of a box on a spring, where the friction completely prevents the box essentially from moving at all, like might be the case if it is super, super overdamped. Right, so the spring can still pull the box back towards the origin, but all the while friction is getting rid of its motion such that when it gets back to the origin, that's where it stops, rather than overshooting it where then it might oscillate and decay away. You can take the other case of overdamped, where you have a box, the spring is still trying to pull the box towards the origin, but it's pulling the box through essentially, honey and wet cement and things that have an exceptionally high friction. So even though the spring is exerting a non-zero force trying to accelerate the box, friction is so effective that essentially it keeps the box more or less stationary, and it slowly but surely pulls the box through that, clay or whatever it's being pulled through. So friction is very, very effective at making the thing not really move at all, as the spring nonetheless still exerts a force until the box gets back to the origin. If I were to make this friction even larger, the green curve could more or less be completely horizontal, but slowly but surely over time start to slowly veer back towards the origin. But you could have it take arbitrarily long if you had friction that was so strong that it could more or less stop the box from moving at all, even though there'd be ever so slight motion because the spring is nonetheless exerting a force on the object. So its velocity would be kept very small, and it would take a very long time for it to get back to the origin. So critical dampening is important in everyday life. If you want to design energy efficient doors, for example, that are on essentially springs that cause doors that shut on their own, you want to adjust the value of the spring ideally so that it matches the so that it is critically damped, so that when the door is pushed open, it will swing back closed on its own, but it will do so as quickly as possible. Because again, if you want to think of an energy efficient door and you're trying to air condition or heat up a room, you want that door to shut as smoothly as possible without it kind of overshooting, which then the door might slam shut on itself. That can't be good for the long-term health of the door. But if it can bring itself to a close as quickly as possible without overshooting, critically damped is kind of what you want to do. And then the door is open for the shortest amount of time, which then is more energy efficient if you're heating or cooling a room. So there are motivations of trying to understand critical dampening, because you want to ultimately set these things up to be critically damped. All right, let's move this guy out of the way. All right, so that's damped oscillations. Now what about driven oscillations? And these are the cases where you might have x double dot plus 2 beta x dot plus omega naught squared times x. But instead of it being a homogeneous equation, there might be some driving force or driving function. I'll put force in quotes because dimensionally this really is units of acceleration. It's really force over mass in this case. But you can imagine that acceleration arising from some force that's being applied to the oscillator, right? A pendulum swinging in the wind, you pushing a kid on a swing. These are all kind of examples of what's going on when there's a driving force. The driving force could be continuous, like a wind, or it could be discrete. Right? It could be you give an impulse, as you push a kid on a swing. You're not pushing them continuously, but your force is non-zero for a finite amount of time, and then it drops back down to zero again. You could imagine even the extreme limit where it is literally at an instantaneous moment in time. Right? That's usually modeled with something called a Dirac delta function, where you just have a quick impulse, that happens over an instantaneous moment in time. So in general, we know that the solution has to be the homogeneous solution, plus then we have to dream up or find or have a way of figuring out some particular solution. And if we can write both of those down, we're done. And that is the general solution to this oscillatory equation, even when there's a driving force which itself might be a function of time. But then we also know of why this particular solution in this case could be very important, because we also know that when beta is greater than 0, that, go back to my equations, let me see, luckily I minimized it. Then in the case of any case where there is dampening, critical, overdamped, underdamped, doesn't matter, all these cases, eventually this homogeneous solution, which is what I'm really plotting here, go to 0. So we know that the homogeneous solution goes to 0 eventually, once enough time has passed, so that we know the general solution eventually just becomes the particular solution. So this is the long-term oscillatory motion, or maybe it's not oscillatory motion. So this driving force ultimately does decide what sort of motion ultimately results. Also, it can play a very important role depending on the exact value of beta. Even in the cases where beta goes to 0, you can imagine that the driving force could also potentially lead to things going unstable. Think of resonance is what we'll get to towards the end of this lecture. Right? You can imagine pushing the kid on the swing so much that they start to then go around 360 degrees. That would be an unstable solution. Probably not very good for the kid either. So in trying to understand this more general case where we're allowed for driven oscillations to occur, we need to have some sort of general approach to figuring out the particular solution. Because if we can understand, again, the particular solution, that ultimately is going to tell us what the oscillatory motion, or what the motion rather in general, looks like in the long run. Now, particularly, we're going to restrict ourselves a little bit to only consider driving forces that are themselves oscillatory. So particularly we're going to be interested in forms of f as a function of time that are themselves oscillatory. i.e. f of t is going to be something like some constant f naught times cosine of omega d times t, where omega d might be what I call, say, a driving frequency, perhaps. This actually will play a very important role, and we'll see in the next module that actually we can describe any sort of general driving force in terms of a bunch of oscillatory forces, something called Fourier series. But these themselves arise very naturally, in a lot of contexts as well. So studying them in their own right is useful, particularly here. So we're going to consider cases where this kind of driving function on the right-hand side is itself f naught times cosine. And again, if we can do it for cosine, it's going to be identical for sine. So we're going to be able to do it for any sort of kind of trigonometric oscillatory motion. You might expect, since the solution for this sort of differential equation, which is typically either exponentials or sines and cosines, that if I plug in a cosine on the right-hand side, it might be the case, you might expect, that we should be able to do this analytically. Of course, if I give way too complex a function on the right-hand side, usually only a computer can do this for us. But if the function on the right-hand side is itself just a simple cosine, perhaps analytical solutions are still possible. Because when we have an analytical solution, then we can explore, by tweaking variables, we can see kind of what goes on. For example, what happens when the driving frequency matches the natural frequency of an object? That might be a case where you are pushing a kid on a swing, but you're always pushing them at exactly the same time, i.e. maybe right when they're about to start descending on their trajectory back towards the other side of the swing set. You might imagine that results in different motion than if you were to randomly push on a kid, at any point in its oscillatory motion. But if you're always pushing at the same spot, well, that's how you get the kid to rise higher. What's going on there? So in order to do this and study motion where the driving force is itself oscillatory, we can solve this, of course, with sines and cosines. One way to do this, which is not really the way we're going to do this, but I think it's the way your book does it. One way to do this is solve instead the case where the force is not just a cosine, but you write this as ei to the omega d times t. So you treat it as a complex exponential instead, which, remember from Euler's formula, is cosine of omega d times t plus I sine of omega d times t. And why it's useful sometimes to do it this way is if you solve it with complex numbers, using all the various fun properties of complex numbers that you have, it's easy to deal with exponentials. You can solve this kind of general solution, and you'll likely get a solution that is complex, but then you just look at the real part. And since the real part here is the cosine part, that would then give you the solution if f of t was just f naught times cosine. So often a general approach is to solve it with complex exponentials and then just look at the real part or just look at the imaginary part, and those will give you two particular solutions for two real cases where the driving force was either a sine or a cosine. We're going to, in essence, do something like that, but a little bit backwards, that I find to be a little bit more easier to follow. But first, on that note, we're going to do a quick aside because I'm going to need this result later. If the force F sub t is equal to, and I'm just going to write it as capital F e to the I omega times t, I'm going to drop the d's. So if there's no subscript, that's the driving frequency, but I'll still write a 0 for the natural frequency, just to make my math look a little cleaner. So in this case, a reminder that f is some arbitrary constant, but is given. Right? It's not a constant of integration or anything like that. It's something that's known, but right now I'm just treating it like a constant. And I want to guess a particular solution such that when I plug it into that equation at the top, here I'll even highlight it, right? Ultimately, I'm trying to solve this. That when I plug in a particular solution, I get f times e to the I omega t on the right-hand side. So again, I might assume then that if I want to get an exponential at the end of the day, I might guess that my particular solution is itself also an exponential. So I might write as a sub particular I omega t, where this a sub p, remember, is not a constant of integration, but is nonetheless a free parameter that I then have to match, and probably is going to depend on, you know, capital F and maybe omega and stuff like that. I just hit my knee. Ugh. So let's see, if we assume the particular solution is some constant a times e to the I omega t, I could plug that into the differential equation. Right, so I plug that in. Maybe I'll recopy it here. Plug it into this and hope that at the end of the day it turns into the right-hand side. So the nice thing about exponentials is that the derivatives is pretty simple. So this looks like it's a sub p omega squared, actually negative omega squared, because actually let me just write it out explicitly. When you take the derivative twice, right, and I times omega drop down and drops down twice, because you're taking the derivative twice, plus 2 beta a sub p, and I omega drops down, and there's e to the I omega t. Then there's omega squared a e to the I omega t. And we want at the end of the day this to equal f e to the I omega t. The nice thing about assuming the solution also looks like e to the I omega t is now there's an e to the I omega t everywhere. I can cancel those out. And it looks like I have an expression that then I can solve for a. So then a particular solution, so then a sub p looks like at the end of the day, if I set it equal to, it looks like f all over, then you have to think of what's going on here. In this case, this becomes negative omega squared, because I squared is -1. So then, and then this is, but that's not the same as omega naught, but I can combine those, so it looks like it's omega naught squared minus omega squared. But then there's the 2 beta omega times I. And that's all on the left-hand side, so that when you ultimately solve for all of this, essentially you can divide through all that stuff to isolate a sub p, and you get something that looks like that. So then the particular solution in this case looks like it's omega naught squared minus omega squared plus 2 beta omega times I. Notice this thing is itself a complex number, all multiplied by e to the I omega t. And that is the particular solution, right? That would give you a particular solution when the right-hand side is f times e to the I omega t. We will need this in a second, so maybe I'll highlight it just so that we remember it. Right, the particular solution with the left-hand, the right-hand side rather, being f e to the I omega t. But of course, ultimately what we wanted to solve for is I want to figure out the particular solution when the right-hand side is not e to the I omega t, but when f sub t is, we said it was f naught cosine of omega t. Again, remember, no subscript means it's the driving frequency. Well, it turns out everything we just did actually can be very helpful, because I could again use Euler's identity and note that I can write the cosine as e to the I omega t plus e to the negative I omega t, all divided by 2. That is an identical way of writing cosine. So I'm writing the thing that's a real function, cosine of omega t, as the sum of two complex exponentials, but I know that when I add them together, I get something that is real. And again, that's easy to prove, right? Just remembering that e to the I theta is cosine plus I sine theta. You know, replace theta with omega t, you can easily show that e to the I omega t plus negative e to the negative I omega t divided by 2 is the same thing as cosine. However, now here's where the previous result is useful. I know when the right-hand side is something like f naught over 2 e to the I omega t. I know what that particular solution looks like. It looks something like that. But instead of capital F, I might just replace capital F with f naught over 2. I know when the right-hand side is something like that I can do the same thing. I can also write it as something like this. Again, replacing f with f naught over 2, but then noting that since there's this negative sign here, I might replace this with minus 2 beta omega times I instead. So the nice thing is that we already know the particular solution. Right, the particular solution in this case is, let's see, so for the first exponential, it's going to be something like omega naught squared minus omega squared plus 2 beta omega times I, all times e I omega t. And then, let's see, I should put some brackets around this. But then there's the second exponential where I expect it's going to be f naught over 2. And it's going to be omega naught squared minus omega squared minus 2 beta omega times I. And again, you can just go through the derivation again if you wanted to convince yourself that that is the case. And so I know then for when the right-hand side is just f naught times cosine, that this big ol' mess is also a particular solution. So let's see if I highlighted this. That is the solution when f sub t is f naught cosine of omega t. Now the thing that's not obvious right away is whether or not this thing I've just highlighted is a real function, right? I plugged in f naught cosine of omega t on the right-hand side. That is a real function. So I should expect that the solution is also real. Though in this case, there's all these i's flying around. There's e to the I omega t, e to the negative I omega t, and there's also these i's in the denominators of the coefficients in front too. But again, we expect that the solution should be real. So I should expect that I should be able to simplify this in some way such that the answer ultimately is a real function, such that all the i's should go away. Since I'm at the bottom of the page, let me copy this. So essentially now what we're going to do is a bunch of simplification. All right, so just to summarize, we expect x sub p of t should be real. Since f sub t, which was just f naught cosine of omega t, itself is real. So how do we simplify this? Well, we can make the coefficients out front real, or at least attempt to start the process of making them real, by rationalizing the denominators, the complex denominators. which, just as an aside, to remind ourselves from high school probably, I feel like I did this in high school, that if you have something that looks like this, you always can write any complex number as a number plus a number times I. This is 1 divided by that, so it's not quite in that form, but you can rationalize it by multiplying by the complex conjugate on the top and the bottom. This then becomes a minus b sub I on the top, and the bottom becomes a squared plus b squared, remembering that I squared is equal to -1. And the cross terms cancel as a result. So I can take both of these things, I can take the things in brackets, multiply by their complex conjugates, which notice actually that they are complex conjugates of each other, which is going to be helpful because then this is ultimately going to simplify to all be more or less the exact same thing, at least in the denominator. So when you do that, and let me just jump right to the end rather than having you watch me do math. The first one at the end of the day, right, there's still the f0 over 2. Then the first one, when I multiply by the complex conjugate, right, so I have omega naught squared minus omega squared. Complex conjugate is 2 pi, or 2 beta omega times I. Then the denominator ends up being omega naught squared minus omega squared, all squared, plus 2 beta omega, all squared. And that's still being multiplied by e to the I omega t. And then that's being added to it. So got the f0 over 2. You actually got the same denominator, which is helpful on this one as well. But then the numerator looks close but not exactly the same. Omega naught squared minus omega squared plus 2 beta, because it's the complex conjugate of what used to be in the denominator. Then that's all being multiplied by e to the negative I omega t. At this point, you might be thinking we have not made anything better. We've made things worse, if anything. This denominator, so I don't have to keep recopying it, let me just define it to be capital D. So whenever you see capital D, it's that thing in the denominator. So it looks like x sub p, right? There's an f0 over 2, which I'll factor out. Then it looks like there's kind of a omega naught squared minus omega squared minus 2 beta omega times I e to the I omega t plus, I factored the f0 squared out, or the f0 over 2 out, plus 2 beta omega I, that's all being multiplied by negative e to the negative I omega t. This is all over d, because we have a common denominator. I factored out f over 2. We're getting there, getting closer. Notice there's some parts that have omega naught squared minus omega squared on the top. And then there's some parts that have 2 beta omega times I on the top. So let me rearrange again. So there's an f0, and then over d, I'm going to factor out, but I'm going to let the 2 come back in. And there's an omega naught squared minus omega squared. And then that's all being multiplied by, there's the e to the I omega t. And then there's also a plus e to the negative I omega t all over 2. And then there's the 2 beta omega times I. And then there's also e to the I omega t, but then there's a minus e to the negative I omega t all over 2. And why am I doing this? Because again, we can use the Euler relationships that I know those exponentials, the sum of them divided by 2 is cosine. And it's not too hard to also convince yourself that the difference of the 2 divided by 2 is sine. So this ultimately, which is good, we're getting rid of some of the exponentials. So this is f naught over d. Then it's omega naught squared minus omega squared times cosine of omega t plus 2 beta omega times I times sine of omega t. So my life is, oh, sorry, I've made a mistake. This I also plays a role as well. So it's that, yeah, let me just write it off to the side. Cosine of theta is e to the I theta plus e to the negative I theta all over 2. But sine of theta by the Euler formulas is e to the I theta minus e to the negative I theta all over 2. And then there's an I out front as well. So that's where we can make those relationships pop back to get everything to work out correctly. No, sorry, there should be a negative out front. Oh, I've made multiple mistakes here. So this should be negative, notice. Because again, this was negative 2 beta I multiplied by the positive. So this negative better be out here, so that ultimately is the same thing here. But then this negative, when you throw it in with that negative, is in a positive, so that then matches this term here. So the relationships here by the Euler identities then turn all those things into sines and cosines, which makes this I go away as well. So this is just still 2 beta times omega times sine. Sorry for that. Lots of math. I'd be shocked if that's... I'm going to have to watch this one carefully to make sure I didn't make any additional mistakes. But notice what's happened. This thing at the bottom is all real. F naught d, right? D was real because d was just that thing highlighted in blue. That's all a real number. All the complex exponentials, the complex i's have disappeared. Furthermore, through some trig identities, again, when you're adding sines and cosines, you might expect that there's some trig identities. You can simplify this even more, such that this particular solution in this case ends up being f naught divided by the square root of d, all multiplied by a single cosine of omega t minus phi. And again, this is just really trig identities that are playing a role here, where phi in this case, if you're curious, is the inverse tangent of the 2 components of d, 2 beta times omega, all divided by omega squared, omega naught squared minus omega squared. But again, the takeaway is that we've succeeded at writing the particular solution as this thing I've highlighted in blue, with D being given by the highlight above. And that is a particular solution. And I think I'll just rewrite it for completeness. All right, so it looks like we got F naught all over the square root of omega naught squared minus omega squared all squared plus 2 beta omega all squared. That entire thing is in the square root, and that's all being multiplied by cosine of omega, the driving frequency omega t minus phi. Where it's just some phi is just some phase angle. Give me beta, give me omega naught. I can plug those numbers in, get an angle. Maybe that's actually what I should be highlighting. The particular solution, why were we doing this again? When the right-hand side was F naught cosine of omega times t. Give me a driving force that itself is oscillating as it pushes on the oscillator. And this is the particular solution. This is the actual motion that the oscillator will follow as a result. Notice it also oscillates. So after the homogeneous solution you think might damp away because there's friction, because there is a beta, assuming beta is non-zero in this case. It doesn't have to, right? It couldn't be zero in this case. You could plug in beta equals 0 too. But the resulting motion would be some sort of oscillatory motion as a result. Now, there are a couple of reasons why this is going to be super, super helpful. Particularly, we're going to be able to see that for more general periodic driving forces that aren't just simple sines and cosines, we're still going to be able to write things in terms of a bunch of sines and cosines. And now that we've solved this particular case, where f naught cosine of omega t is the right-hand side, we have essentially done it for any kind of sine and cosine function that there is. Right, cosine of 2 omega t or 3 omega t or sine of omega t. We can write down analogous answers for those particular solutions. So that if I had a function that was, say, a sum of a bunch of sines and cosines, I can then write down a particular solution for each of those sines and cosines in that sum, and then when I add all those particular solutions together, I get my general particular solution as a result. So that'll be the next module. The last thing I'll add here, and then I'll show some simulation examples, is let's look at this overall amplitude again real quick. So this particular solution amplitude we said was f naught, and then it's all divided by omega naught squared minus omega squared all squared plus 2 beta omega squared all in the square root, all in the denominator. This is the resulting amplitude of the oscillatory motion once this oscillatory force is applied. I'm applying a cosine force to the object. The homogeneous solution damps away. This ultimately then is the amplitude that the object will have as it oscillates back and forth as a result of this oscillatory driving force. And we can already start to notice interesting things can happen. Particularly, we get this thing called resonance. And resonance occurs when beta is small and omega is approximately equal to the natural frequency. When the driving force frequency is mimicking the natural frequency, which, remember, the natural frequency depends on the properties of the system itself. Spring constants, masses, gravities. Where the driving frequency is whatever is set up by the machine, or how frequently you're pushing the kid on the swing. That's set up by the device, whatever is creating this driving force. But notice what happens is that f naught, right? Well, that's also can play a role here, but let's assume f naught is fixed. Right, it's some machine that's applying some sort of force at a certain frequency that you're fine-tuned to. So you could ask, when is this amplitude the largest? Right, this amplitude is large when the denominator is small. The denominator is the smallest when, well, if the driving frequency is equal to the natural frequency, then this first part goes away, right? This just becomes 0. And then you're left with something that only depends on omega and beta. So then if you have something that just is 2 beta times omega, then when beta is small, then this also becomes pretty small. And as a result, when you have both this and this entire expression gets pretty small. And as a result, you get a very, very large amplitude at the end of the day. So I have an expression here that kind of shows some examples of what we mean by resonance. So what's being plotted is the amplitude squared. Don't worry too much about y, but it's the amplitude squared that's being applied. So the square of the amplitude that would result. I'm not sure what I just did. And then there's a given kind of natural frequency of 2, and then the numerator, this f naught, I'm setting equal to 1. And then the horizontal axis is the driving frequency, right? So just omega in the equation divided by omega naught. So when it's 0.5, that means this divided by this equals 0.5, but since omega naught is 1, that just means when the driving force is equal to, the driving frequency is 1. When this ratio is unity, that means they're both the same thing. So this is when the driving force is equal to 2. Over here is when the driving force is equal to 3, that sort of thing. And we're seeing what amplitude we expect. So essentially I'm just plotting that function for different values of omega drive, and the different colors give you 3 different values of beta. So the green is the case where you have a large amount of friction, where beta is pretty big. And notice the amplitude is pretty small, and it does bump up a little bit around this kind of resonance spot, but then dies off. Doesn't get that big. Make friction a little bit weaker. Notice it kind of dies off on the outskirts, but when you get around the natural frequency, the amplitude increases as a result. Make friction really small, you start to see what's happening, right? You get very, very large amplitudes around when the natural frequency and the driving frequency are the same. You can figure out, it's a Calc 1 problem to figure out the max. I don't think the max actually occurs exactly when they're equal to one another, since there's an omega in this term as well. But clearly it's when they are very close to one another that this starts to occur. And so this is resonance. This can be very bad if you're, say, building a device that has some natural driving forces that are being applied to it. You don't want hitting resonance might cause the thing to oscillate perhaps unstably, which could result in some bad things happening. The kind of famous, though slightly apocryphal example is that one, I'm blanking on the name now, the bridge that collapsed. Let's see if we can look it up real quick. Bridge collapse, frequency. What's it called? The Tacoma Bridge, yes, thank you, Google. The Tacoma Bridge, which had that kind of oscillatory motion, and it kind of looked like, essentially, it is in effect similar in idea in that essentially, motions of the wind caused, the bridge to kind of occurred at the natural frequency of the bridge, and the bridge started to kind of oscillate back and forth, and it started to twist and distort, and eventually collapsed in on itself. That technically isn't the exact same thing, but it's a similar kind of idea. Essentially, some sort of resonance was hit, and as a result, the bridge kind of collapsed on itself. Not because of anything anyone did, but kind of these natural oscillatory motions got bigger and bigger and bigger without them being damped away, which can occur very much so when you're hitting these kind of resonance locations. So let me show some examples of this, which I can do some simulations kind of on the spot. Let's see here. Let's look at some cases where there is no drag. There's not supposed to be drag, so what is going on here? This I think should be 0. Let's see, what is being plotted? Oh, that's why it's not doing it right. There we go. So let's just look at some examples of kind of oscillatory motion with and without driving forces and with and without friction. So ultimately the black curve is going to be showing you, I'll change this, also is going to be showing you the motion that you ultimately see. Let me just, instead of calling it no driving in the legend, let me just call it resulting motion. Rerun the simulation, it looks like that. Whereas a function of time, right, you might imagine some oscillatory object, right, maybe it's a box on a spring, and it's oscillating back and forth between 1 and -1. Its kind of natural frequency, I think, ends up being something like 2 seconds or something like that. But in this case, the driving function, the right-hand side of that differential equation, maybe we can put it back up on the screen real quick. Let's see, what were we ultimately solving? That thing in red there, right? If we're solving this expression, but we're going to not have dampening for a second, and we're going to look at different driving forces. So in this case, there's no driving force. Notice the blue dashed line is just going to be 0 in this case. So there's no friction, no driving force. Unsurprisingly, you get oscillatory motion as a result. Now let's keep friction at 0, but let me give some driving that takes a very long time. Actually, I want to go even shorter than that. Let's do something like this. There we go. So again, no friction, but there's a driving function, which again doesn't have units of meters, but forgive me. That is kind of going over very long periods. All right, it seems like it's about 15 seconds or so for it to kind of complete one oscillation, which is much longer than the period of oscillation, the natural frequency, the natural period of oscillation that occurs for the oscillator itself. And notice what's happening in this case. The oscillator is more or less still oscillating at its natural frequency, but notice that the kind of driving, the very gradual driving force is kind of making the entire thing kind of sway with the driving function. So kind of it's oscillating back and forth, but then its entire thing is kind of going up and down, oscillating with this very gradual driving force that's being applied. Now if I up it so that it's oscillating a little bit faster, but not in a number that's commensurate with the natural frequency. Right here, notice I've made the oscillating kind of occur more rapidly, right? Kind of completes it in every 7 seconds or so. And notice what's happening is that it's kind of getting mixed up with the oscillatory motion of the actual oscillator. It's trying to naturally oscillate, but on top of that, it's kind of natural oscillations. The driving function is kind of giving this kind of screwy oscillatory motion, which it is kind of oscillating, and it does seem like it starts to repeat itself, kind of going from here to here. But it definitely doesn't look like a cosine function anymore. Kind of now looks like a superposition of sines and cosines. Then if I make the driving frequency exactly half the natural frequency, it's not quite resonance, but essentially the natural frequency, right, it wants to complete an oscillation every half period of the driving function. So notice here they're kind of aligned, then here they're anti-aligned, here they're aligned, here they're anti-aligned, aligned, anti-aligned, etc. And notice kind of what's happening. It seems that when they're aligned, you get a big amplitude, right? It goes all the way out to 1. When they're anti-aligned, they're kind of working against one another. Right? The spring wants to go to the right, the driving function is trying to push it to the left. You get a smaller amplitude as a result. Then it kind of oscillates back and forth between that. Now let's up it a little bit more. So we're getting close to hitting resonance, but not quite. So here we're not quite at resonance yet, but we're getting there. And notice before, initially everything was kind of oscillating between 1 and -1. Notice that the amplitude is getting bigger in some cases, right? It's going up to about 1.5 to -1.5. Then it decreases, then it gets big again, then it decreases. And so we're getting close to the driving force being kind of in resonance So here's where we're very close to being in resonance, but not quite. And notice what's happening. The driving function is always when it's pushing to the right, the box is also moving to the right. And so the amplitude itself is growing and growing and growing, and this starts to make people nervous because the amplitude looks like it's getting bigger and bigger and bigger without it ever being able to stop. And indeed, if we were to go at the actual natural frequency where we expect resonance to occur, remember it's supposed to oscillate between 1 and -1, and now it's going all the way out to 10. And if I made this plot go even farther out in time, the amplitude would just keep getting bigger and bigger and bigger. Because in this case, there's no dampening to stop it from getting bigger and bigger and bigger. So it's the kid on a swing that just keeps going higher and higher and higher. This is resonance. Then if I go at a frequency that's above the natural frequency, it starts to get kind of messy. This is a little bit bigger than resonance. So you still get amplitudes that are kind of flying all over the place, but since the driving function is oscillating back and forth so much, it's starting to get to the point where sometimes they're kind of aligned with one another, but then sometimes they're kind of anti-aligned with one another. And here they're anti-aligned, here they're kind of aligned, but not really. Here they're kind of anti-aligned, anti-aligned, kind of aligned in this case, kind of aligned in this case. As you increase the frequency more and more and more, you get to a space where essentially there's an equal number of times when they're kind of in the same spot versus when they're anti-aligned versus when they're kind of offset. And so it's kind of more, you're just kind of hitting things at random in this case. So sometimes you're kind of working with the kid as it goes, down on the swing, but sometimes you're pushing on the kid while they're moving up or while they're kind of, momentarily stationary. And so notice you're back to having the amplitude kind of be somewhere between 1 and -1. You're not getting amplitudes that are getting very, very big. Or I can even make it extreme in this case. Yeah, it's kind of, I made it too extreme. It's kind of too hard to see, but the black line you kind of can see. Let me make it easier to see in this case. Let's see, alpha equals 0.3. Let's try that. There we go. All right, the driving function essentially is always working with you, and it's always working against you at random spots. And so essentially it's kind of canceling itself out, and it looks like you're getting something that looks more or less like it's back to being simple harmonic motion with some slight deviations, right? These kind of curve up and down ever so slightly. But essentially, the driving force is kind of random noise acting on the object. Now let's go back and throw friction back in. So here is the case of kind of long motion, but there's no friction in this case. Let me throw friction in now. And what do we expect to happen? Well, the friction is going to get rid of this kind of natural oscillation, because remember, let's just go back here. Oh, conveniently it's already on screen, right? What we said is that this is the general solution, but when there is friction, the homogeneous part is going to go to 0. So ultimately, at the end of the day, I should get a solution that more or less matches the driving force in this case. So let me put friction now back in. When I run it, let me make friction a little bit weaker so it's a little easier to see. Notice what's happening. Instead of the black line having all those little oscillations on top, friction is damping away those oscillations, and that's essentially, you're seeing some of it still here. This is an underdamped system. And once those go away, notice the solution just essentially follows the driving function as a result. And if I make the driving frequency a little bit higher, maybe something that's close to resonance. Again, notice you get some kind of weird stuff that's going on, but then after the homogeneous part dies away, it essentially looks exactly the same from here on out, but it's matching something that's more akin to the driving function instead. And then if we do it exactly at resonance, let me make friction a little bit weaker so it takes a while for it to die off. Right, notice the amplitude, this is at resonance. Notice that at resonance, you've got amplitudes that are growing, but it looks like it's plateauing ultimately, and it's not actually getting out to amplitudes that are getting bigger and bigger and bigger. They are getting big because you're still at resonance, but it's not growing uncontrollably. And if I make friction bigger so that that dies away faster, right, notice that the amplitude grows initially, but then it kind of plateaus at the resonance amplitude that we would expect. Again, the amplitude that's given by that expression there, and that we matched, kind of relates to this particular function as well. So this amplitude here might be matching kind of what you would expect for the particular parameters that are being used at this resonance location. So lots of things can happen. It's kind of fun to play around with, kind of easier to work through on a computer. So I showed you these kind of examples, and we'll probably do some of these in class as well. But again, we took all this effort to figure out how to solve in the case where you had a cosine function on the right-hand side. But as motivation, now we want to be able to understand kind of what's going to be the oscillatory motion that I get when the function is not a cosine function like this, but when the oscillatory function is something like, maybe it's like pushing a kid on a swing, where you have a non-zero force, but then it goes to zero. Then when the kid comes back, you have a non-zero force, then it goes to zero. Non-zero force, then it goes to zero. That's a periodic oscillatory sort of motion, where the force is kind of non-zero for a finite amount of time, but then it goes to zero. Right? Or something you see in like signal analysis, kind of a sawtooth driving force that does something like this. You know, what sorts of oscillations do I expect in that case? Or what if it's just something super general, where I have something that looks kind of like that, but then I can imagine that it might repeat itself, you know, periodically. You know, none of these, except that first one in the upper left, look like sines or cosines, but it turns out I can take something like this that has a bunch of squares, and I can write it as a sum of a bunch of cosines and sine functions. That is what is called Fourier series. Like Taylor series, where you can take any function and turn it into a polynomial, Fourier series, we can take any function and turn it into a bunch of sines and cosines, which is pretty cool. And we'll do that next time.